Very good. So we have begun. A couple of little housekeeping notes, which I call them, is just stuff that I've done. You should have gotten recordings, 3 of them. When I listened to those, I realized with that lab practical, people have been pretty occupied. So not a lot of people have listened to them, but I can see how many times they've been listened to. You know, if you're lucky with any YouTube channel that you that. So, but make sure you get. It's important for next because next week we're here doing the exam, and then unfortunately because we have a weekly class, we'll find time. It's better to do the exam and then do a second half lecture the other way around because you can't focus on. You're too busy not listening to the lecture because you're trying to study again for the exam. So that's kind of the housekeeping nugget that's there. Email me, get in touch with me, have questions, whatever. I mean, it's we'll see. Our number keeps dwindling here, but I understand that. We'll see who's here next week. That'll tell the tale. Nevertheless, you might remember last time we had just finished osmosis. That was the end of that particular PowerPoint. I have just mailed you. I mailed them to you before. These the remaining ones that are in this sequence that I like to use for this. And so this is what we're covering today. I sent you all 3. Whether we get into that third one, I do not know. It's very hard to tell how much to put into a particular week of me talking to you, but we shall see. Just double check, make sure I'm on and recording. I am on and recording. With that, we'll begin. So if you have any just shoot me an email if you have a question in class, whatever. I'll try to, because all of this is all, again, once you're going to see a little mention here of some of these cell connectors, but I'll reinforce, what you really have to know is just some basic definitions of things like desmosomes and gap junctions and tight junctions, and I'll get into that along with the roles of the proteins. That's a very limited part of this exam. 65 questions, multiple choice, true, false, matching types, number pencils. It will not let it will. If I get my pet peeve is pens on those things because then it won't score and it throws off all the metrics when I try to figure out averages and things like that, the statistical portion of it. So because I may have a couple of these hiding around, but not a lot. Necessarily drive me crazy. It's a pet peeve. I'm entitled. With that note, let us begin. What we had dealt with before was called passive transport. There was no, we utilized basically concentration gradient and the power of it. The body is very, very designed, that's the right way to phrase it. The body spends energy very, very limitedly. When it does spend energy, it tries to optimize or maximize the energy. I mean, it's if you're running a business, you don't want to spend something unless you're going to get. And the body's not a whole lot different. We don't use our energy resources frivolously. So frugal might be a better word to express it. And so when you see what's called active transport, anytime, that's another word you'll see for that is pump. We're going to study here and acquaint you with the most commonly used, the most well-known pump in the whole body, the most well-known form of active transport, which is called the sodium-potassium pump. Today's presentation is very important because it sets the foundation for everything that has to do eventually with the vast bulk of what we study. The entire second half is dedicated to muscle and nerve physiology. Certainly anatomy, but a lot of muscle and nerve physiology. I cannot tell you how important this aspect is in what you're looking at today with regards to. There's a wonderful animation. That'll be part of it. A lot of times we'll also talk about things called endo and exocytosis. How we bring in bulk transport. I don't have a little item to bring into the cell. I got to have a big item to bring into the cell or spit out of the cell. And so when you have that, you literally have to open and encase it in membrane, and then when you have to spit something out or expel it, or the proper word is secrete, S-E-C-R-E-T-E. So like secretions like saliva or mucus are secretions. Effectively, they're being produced in the cell and spit out of the cell. And this is called exocytosis. Those are called vesicular transport because we're encasing them in membrane. And another name for those membrane-bound structures, sort of spheres of membrane, are called vesicles. So that's where the term vesicular transport. To create those and open and close them, bring stuff in and put stuff out, requires energy. So that's why these are both considered under the realm of active transport. So both require ATP. Too large for the channels, that's where vesicular transport comes in. Not lipid soluble, that's the way a lot of the things that you will see have to be brought in. You're going to see different kinds of channels that bring that in, different kinds of ways that that's transported into the cell. And it particularly, we have to expend energy, as you will see, to move it up or down, move it up against the concentration gradient. Talked about that last. The concentration gradient is powerful. It's very difficult to push things where effectively Mother Nature says, we got enough here. You keep colliding with things and it keeps pushing back at you, hence the energy expenditure. So we use the term pumps, and you're going to see this solute pump, specifically and reversibly, meaning once it's bound, it does whatever its job is, bringing it in, pushing it out. And you're going to see the one we're going to look at does both. Almost not quite simultaneously, but effectively simultaneously, bringing in a couple of potassiums while it's kicking out 3 sodiums, all at the same time. So, and the reversibility means it's not used up. We use it again and again and again. Effectively, it's an enzyme that we can continuously use. And it's found in, you're going to see this in all of our cells. It's just used a lot more in nerve and muscle cells. You're using them right now, but your nerve and muscle cells are using them the most. Your nerve, of course, of your brain, your muscle cells, if you're writing on a keyboard or on your laptop or your pad or making mechanical notes or whatever. Okay. So moving on. So specifically and reversibly, and because of the energy expenditure, when things flow in or things flow out and we're pushing them in, or pulling them in and pushing them out, and expending a force, we create almost a passageway. We create a certain amount of current. And not current in an electrical sense, but current like in a water sense. Okay? And we can utilize that. And we can either utilize that to bring along other things and push them in, or either pull them in or push them out. Another name for that is called SYM, S-Y-M. I prefer the term, and a lot of textbooks use this. It's easier to understand, called co-transport. A lot of the times you'll see that when we are in the urinary tract, we reclaim sodium. You know, we get rid of a lot of sodium, but we reclaim a certain amount of sodium. When we reclaim the sodium, at the same time we bring glucose in, because you don't want to expel glucose in the urine unless someone's a diabetic. And that way they've sort of run out of room, and basically they have an overload of the glucose. That's what we see. We call it spilling into the urine. That's a form of co-transport. We're using sort of the amount of energy we put into bringing in the sodium, and we basically have created enough of a passageway or enough of a flow to bring glucose along for the party. So too, we can go in the opposite direction. And if you think of the best analogy is like if you're at the ocean, particularly the Atlantic, okay, it has a very powerful undertow. Little kids have to be very careful. You're standing and all of a sudden the wave comes in and you know it goes back out, and the next thing you know your feet are buried. That's the undertow. And if you didn't know, it's a whole lot more. Pacific is considerably milder. It has giant waves in certain areas, but in general, it's a little bit milder with regard to that degree of undertow. So that's why there's a lot of erosion on Atlantic beaches. Like if you go to Ocean City, they're always having to reclaim sand that's getting pushed out, do that kind of stuff. Just is. For beach areas, and a lot of us have gone to on the East Coast. The Delaware beaches and the Maryland beaches, etc. I never let that flow out. Here's the wave coming in, it pushes off something firm, and then what happens? It pulls sand and stuff back out with it. That's antiport. You're going to see, when I talk about this down the road, in AP2, that's going to be how I'll be presented with you how the heart works and what causes the valves to close. A lot of that has to do with forces going against it and creating secondary waves. It has a lot to do with how we maintain our blood pressure when you get into that kind of a discussion. So as I'm trying to set the frame for all of you to understand this. It's little bits, and I hope whoever teaches you AP2 next term, at this point I don't know my schedule, but is it likely to be? No, I typically do more micro in spring semesters. I do my advanced physiology with the majors in the spring typically. So, but they're called antiporters. So anything like that, when we're moving, particularly against the concentration gradient, it requires energy. So when we talk about primary active transport, that's something you're going to see with this, what we call sodium potassium pump. That's a primary use. We're using the ATP directly to move molecules either in or out. Secondary is that indirect one, where we're using the residual aspects of that flow to either bring stuff in or push stuff out. So those symporting, what I call co-transport or anti-porting, are really forms of secondary active transport. From a definition standpoint, for me, the big focus to understand primary active transport. So energy from the hydrolysis of ATP means taking the ATP, that nucleotide, those I power bonds, okay, being held together by extra energy and releasing it, okay. And the classic example, there are different pumps. When you go into AP2 and digestive, you learn about proton pumps. That's how our stomach makes sense. Somebody who's got really acidic problems in the stomach, they may take a medicine called Protonix or Nexium, or they can get Prilosec. Anybody can in a pharmacy. They are proton pump blockers. So it's a well understood mechanism. There are pumps for calcium. The best understood one is the sodium potassium pump. That is more than half of our energy every single day. More half of that massive amount of ATP that we assemble and disassemble every day goes to those pumps. Everything you're doing right now, you're using those pumps. Even a cell that's relatively static, you're going to see very shortly, there's always the flow of charged particles, and you constantly have to reset. It's called the resting membrane potential. So here's the sodium potassium pump. It's an enzyme, nothing more than that. It's just a protein that's embedded. It changes shape, and it makes it easy for us to make sure that we always have extra sodiums and excessive sodiums on the outside of the cell and an excess of potassiums into the cell. All plasma membranes, but especially active nerve and muscle cells. Effectively, how nerve and muscles, to simplify it until we really get to the heart, how they conduct a signal from nerve to nerve or from nerve to muscle, is we have to generate a signal that's telling that nerve, and that basically it's like a wave. So you had a flat pool of water that didn't have any current or any motion, like a pond, and there was no wind or anything. You threw a pebble in the middle of it, and you watch the waves generate. It's like taking something. I can't do it with something that's floppy. It's like you get a sheet out of the dryer and you flap it like that to fold it. Those waves that go through it, effectively, that's what's going along the membrane of a muscle or nerve, and all along that membrane is a quick switching of electrical balance. Because you're going to see consistent. Part of what we call resting membrane potential means, if that's the membrane, it doesn't matter, it could be anywhere along a cell. We're just taking an elongated cell for demonstration. On the outside of the membrane, it's always positive. On the inside of the membrane, it's always negative. The vast majority of our cells, it doesn't change. Always do. You're making tiny corrections, it's always going to keep that relationship. Nerve and muscle cells, under the right stimulation, this can flip-flop very rapidly. And think of that flip-flopping as the way that the signal is carried. That's why this is so terribly important. Because you're going to sit there, you're going to go nuts. Just like 21 steps on how, from me deciding to reach for my marker, and then reaching for the marker, and going all of these steps in order to understand the process. This is part of the basic building block. Because eventually, for me to contract that muscle and grab that, involves that charge rapidly changing and then resetting. Change and reset, change and reset. So this is the basis. It's called the resting membrane potential. I am hopeful, I'm optimistic that this will play sound. I am not guaranteeing it. Sounds like sound. Voice in the wilderness. So so you see, and you can do this as many times as you want. It's doing this stuff. Go back to that. There, all right, you ready?
The human brain alone contains about 100 billion nerve cells called neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
So what you will see, just to give you a look at, I mean, it really gives you a good idea of how intricate the membrane is. Because we all think, it's very hard as a student not to just look at something flat and think two-dimensionally. Like I'm just reading the phone numbers on a sign. Here, you can see not all of these embedded proteins, they're not just in one, they go all through. It's like this giant sheet, this giant envelope, and all of it looks more or less the same with all of those structures. So there's an immense amount of these leak channels. And this is just one example of all of these. And so when you say a leak channel, the channel implies it's always open, and the leak means things move in if they're following the concentration gradient, or out if they're following the concentration gradient, depending mostly on what the concentration is and how many of these openings there are. So I mean, it's pretty well understood. I mean, you can see how vast these things are. And what goes on effectively, so let's say it's a cell, any cell, not a nerve or a muscle cell. Well, why does it have to be corrected? Because the leaks still exist. That's the idea of something being in equilibrium. What they showed you there is, once the sodium comes back in to offset that minus 90, it brings it down to minus 70. Stuff's still moving.
The voltmeter reading
See how it's still moving
70 millivolts.
Continuously. And the fact that it's still, even if she's talking, they're still moving. And so what happens is, to make sure that there's always more potassium inside, maintaining the gradient, and more sodium outside, you're constantly having to go against the force. There still is more potassium inside, but to maintain that gradient, this pump, and you're going to see these are, for instance, these are sodiums being kicked out. There's room for 3. And if you advance it a little bit more, you'll see there's 2 potassiums coming in, 3 sodiums going out, 2 potassiums. You're going to learn to be familiar with that relationship. It's kind of like on the periodic table. You have sodium, which has a smaller atomic number than potassium, even though they're very close to each other. It's like 11 and 19. The difference is that implies size. So if you think of it that way, in the size of that opening in that pump, you have room for 3 sodiums. It doesn't really work that way. You have 3 sodiums, and you can only fit 2 potassiums because they're bigger. And you're going to see this relationship again and again. When we go back to muscle, you're going to see that it's kind of the reverse of that allows a muscle to fire. So I'm trying to give you some context of why this is so terribly important. And this is every single cell. So if you're just sitting there, almost any of your cells other than nerve and muscle cells are kind of like, well, we're expending a tiny amount of energy. But whatever you're doing, thinking, talking, moving, any type of vigorous physical activity, you're devoting a tremendous amount of your energy resources to just maintaining this. Because as you will see, this is critical going forward to maintain what's called the resting membrane potential. It's almost part of the integrity of the cell, without making it seem like it's the be all and end all. But I'm trying to find a way to get the point across so you can appreciate it. So that's everything here. I don't love these illustrations, but this is what they're showing you with the pump. So here you can get this 3 to 2, but these yellow balls, okay, imagine those are sodium that are being pushed out, and these greenish ones are potassiums that are being moved in. And they're trying to show you how, if you follow along with them, how all of that is happening. I mean, so you could take a look at that. The 3 cytoplasmic sodiums bind to the pump protein. The binding induces the energy release, because that's what happens. The ATP isn't magic. It has to do with the sodiums attaching to it, and then that triggers this. And you're going to see something very much like that when you get to how muscle fires and how muscle resets itself so it can fire the next time. And so you can go through those, but I don't go into all of this stuff with phosphorylation and shape changes and expelling and extracellular. My advanced physiology class, that's what we go into. This stage of the game, for you folks, it's enough to know that it plays this pivotal role in making sure we always have, and they gave you a number before, if you add up the millivolts across that membrane, it's right across the membrane. Inside here, it's neutral. Outside here, it's neutral. Right across the membrane, the outside is more positive than the inside, and so the inside registers roughly at what's called -70 millivolts. You don't have to know that so much right away. The -70 will be fine, because I'll put in the units for this. I wouldn't try to fool somebody in a test, and it wouldn't be on this test anyway. You put -70 volts versus -70 millivolts. That's even for me, trying to be too tricky. So secondary depends on the primary system. Okay, indirectly is a good word. You're not moving the other stuff in or out. You're relying on the pump. So dragging, they call it symporting or co-transporting, and that's what I mean. Sugars particularly move this way. And so here they're trying to give you an idea. It doesn't necessarily go through the same channel. Primary active transport here is that sodium and potassium, but it creates changes along the membrane and in other embedded proteins to help bring glucose. And there's the glucose. That's what you're showing. Really, so that's the important part to know about active transport and understanding the vital role of sodium and potassium. Done with that. Moving on. You're ecstatic. I can see you're ecstatic. Enthusiasm is back. Why does everybody look like they're sleeping? I've been up since 5:30 in the morning, and I'm just doing it on caffeine. Vesicles. Again, a vesicle is a membrane container. We think of it two-dimensionally, look at a circle. The reality is like a sphere. Bulk transport. Okay. You're not getting an envelope delivered that's in your mailbox or through a mail slot. We're talking about UPS or FedEx dropping off a big box. Bulk transport. And yes, in order to open and close membranes, it requires ATP. So there's two types that are there. When we're bringing something in, it's like if the cell was going to eat or drink, it would basically have a membrane here and it has the magical ability to be able to take that membrane, because the membrane is flexible, and wonderfully underneath it, there are proteins that can assemble and disassemble. Almost as though if I had an arm sticking out here, that would start to, all of a sudden, that would start to disappear, and the one over here would protrude. By doing that, effectively, it would push against the membrane, the fluid in there, the cytoplasm would flow toward that push, and you start with something that looks flat like that, and the little fingers would start to get closer and closer to the object, and finally engulf it, surround it with membrane, and bring it in. Oh, I love that. It's like, think of it as food. It's sort of, the cell is sort of embracing food. I have an existential relationship with food. I eat, therefore I am. So, moving on. Endo means bringing it in. When you hear the term phagocytosis, it implies it's solid. Pino implies that it's liquid or oils. We do both of these that are there. They all involve receptors. Okay, it's not a random process. Oh, the cell doesn't just go along and go, oh, I just grab this and grab that. Typically, what triggers it, special cells bring in or spit out different things that are there. So when they talk about receptor mediated, it's a very specific one, and the context, the best context I can give you this receptor mediated, what's called endocytosis, is very, very specific receptors, and typically they're tied to genetic things. This is a very important mechanism going forward for folks like you who are really in the early days of your studying of anatomy and physiology. And I assume most of you are going to go on and have to take microbiology and other subjects that are part of it. And understand that I'm presenting it to you what the body is supposed to do, or the cell is supposed to do normally. What happens if that mechanism is effectively hijacked? And that's what viruses can do, what bacteria can do, what toxins can do. All of those things have the capability of being able to take this mechanism and basically, what you will see what will happen, that's how they get into a cell. HIV, even immunodeficiency virus, if it's not taken care of properly, will lead to AIDS, which is fatal. They are not equivalent terms, by the way. Effectively attaches to a receptor, one of these receptors, on the most important white blood cell family we have in our entire body. They're called helper T cells. And when it's latched onto by that helper T cell, effectively, it's like, oh, this has got a specific receptor. The virus is effectively a receptor. It's identical to the markings of something that helper T cell would normally attach to. Yet it's something that can cause someone to lose their life. It's not magic, it's just the way it formed. We see a lot of these look-alike things, and what happens, it doesn't really destroy the cell, it basically takes over that cell line, and that cell begins to clone itself. And it becomes a little factory inside for making more viruses. They infect more cells, and eventually, once that whole line is poisoned, for lack of a better word. If you didn't know, the word virus, when it was coined by Louis Pasteur, means poison. That whole cell line is poisoned, and now it makes white blood cells that don't work. And eventually you get to what we call a critical number of those, and whatever the numbers are known, studied to take them from blood tests, At that point, once it falls before that critical level, it means your immune system effectively is collapsed, and you're now going to die sooner than later. That's the definition of fatal. You know, something is not fatal, it means you have a normal lifespan. If something is fatal, it means it's true. So just to give you an idea of why I have the luxury, or you have the luxury, I have the ability to relate these to clinical phenomena. Because I've only spent half of my career teaching, the other half I've had treating people. So I'm trying to give you some context, because a lot of times you sit back and go, why are we learning this stuff? I'm going to say another word, but in the interest of being polite, the young crowd here, why did my daughter know all of those words so much earlier than I thought she should? It's a great story. This will give you an idea of what I've gone through. There's nothing you can do here. My children are 3 years and 2 weeks apart, all adopted. So it was one Thanksgiving dinner, and the kids basically, what they would traditionally do after Thanksgiving dinner, they would basically go someplace for a while, and they end up lining up. Those are the days when Best Buy and those places had the sales. They'd line up at 3 o'clock in the morning, and the store would open at 6. You go in and grab the flat screen TV, and the this and the that. The kids are all getting dressed up. My boys were 22 and 21. She was 19. They're all together. I said, where are you guys going? Oh, we're going down to the south side. I said to my daughter, it's Mallory. I said, Mal, you're only 19. And she goes, oh, don't worry, Dad. I said, oh, you're not going to drink? No, Dad, I have a fake ID. Like, don't worry, I have a code. I'm not going to get cold. Don't worry, I have my driver's license. I know where to park. Or I have money in my wallet. No, I got a fake ID. Don't worry. Nothing you can do. I've got, all parents have stories that could equal that. Nevertheless, moving on. So here are the different types to become acquainted with. Bringing into the cell, endocytosis. And the reverse of that, it's not like when you have a meal, all of your cells in your digestive tract are going to be bringing stuff in. It's almost like it implies that they're taking some of their membrane and pulling it in, the cell's going to shrink. No. What happens is you will see these structures are brought into the cell, processed very specifically, and either used for digestion, or if there's residue or waste products, they're spit out. And so when they're spit out, that membrane gets reincorporated, the cell membrane. The way we state it is membrane is conserved. So even though the cell's very busy bringing stuff in, sooner or later, it's going to get very busy spitting that stuff out. So it's not like it's going to shrink, and by the same token, it's not going to expand either. So exocytosis is the opposite, exiting the cell. A lot of things, like in your digestive tract, there's certain things that you will bring in, or in the urinary tract, that will not get processed through. They basically are using that lining cell, that epithelial cell, as a passageway. So it doesn't go between the cells, it goes through the cell. It's never, doesn't interact with anything in the cell, and basically exits on the other side and goes into the bloodstream, for instance. That means it's transiting through the cell, and hence the name transcytosis. And understand that it's very complex. Again, when you draw a cell, any of those illustrations of the membrane, it's very two-dimensional. Inside, and I have a pretty unique animation. Maybe we can look at it today, since the sound is working. After the break, I'll try to find out where. Typically, it's on YouTube. And what it demonstrates to you is how complex and how it's ever changing inside the cell. Vesicular trafficking is a series of proteins that form little passageways that bring the vesicle from point A to point B. Okay, this has got to go in and it's got to meet up with something else. We've got to take this to this part of the cell or that part of the cell. It's all chemically controlled. It's not like they have little eyes and things like that, but effectively that's what's going on. It's involving shape changes of those molecules and moving them from point A to point B. It's just miraculous. So you'll see some of these, and you'll see how some of these proteins can assemble and disassemble. When they disassemble, they're soluble. You don't see it. When they assemble, they show up. That's what I mean by it's almost having an arm disappear on one side and growing out on the other side. It's really the same proteins. They're just scurrying along. You can't see them and building themselves up. And when they do, they push on the membrane, and then the cytoplasm flows. What cells do, for the most part, is that's how they move around, or even the organelles inside. Whatever's inside of them is moving around based on subtle shape changes. The analogy would be like a baby. Kind of, before they crawl on the floor, they kind of scooch around. They get on the floor, they've got some head control. They're sort of sliding and slipping, like we've all done as kids, to do that. And then next thing you know, they're up on their knees. And now they're crawling, and now you're in trouble. You're all over the place. We had our 4-month-old great-grandson overnight Saturday. Busy. It's not quite there yet. It's not at scooch. You don't have a 4-month-old great-grandson. Maybe next month. I'll check again. So the opposite of this is called endocytosis. I was getting ahead of myself. This is endocytosis. These proteins effectively are receptors, very selective. It's designed to move glucose in. It's not going to move in something else. It's not going to move a nucleotide. It's just not the way these things work. So it must be able to bind to that receptor. This is the part when you talk about hijacking. Pathogen is a disease causer. It can be anything, but usually the implication is bacteria, virus, mold or fungi, parasites. All of those are things, toxins. Those are all pathogenic entities that can cause damage and or disease in a cell. I'm going to be so tired when I get done here. My wife's trying to drag me out for dinner. It's okay. I can do this. So what happens is these can take it over. And understand, once anything is brought in, the reason we encase it in membrane is effectively to protect it and to protect us. The inside of a cell is very harsh. It's got acids, it's got alkalis, it's got chemicals, it's got salts, all of which could denature or alter something that might be really important. And by the same token, if something inadvertently that I pulled in was bad, like a bacteria or a virus or a toxin, it has the opportunity of saving the cell from being exposed to it. And there's a mechanism at that point. So once it is brought in, it fuses with another vesicle inside called a lysosome. Lysosomes contain enzymes for digestion and defense. So whenever that vesicle comes in, I'll show it to you on the illustration, lysosomes, enzymes for digestion and defense. That's what's in there. And so anything that comes in fuses. It's like two vesicles, and effectively the membranes join and open up and allow the material. What happens if it's a nutrient, if you ingest something that's a food or a nutrient or a building block, the enzymes break it down so it can be useful to either be built in that cell or go someplace else to another cell. Do that. If it's a bad guy, they can destroy it. And at that point, whatever is left over, whatever waste products are excreted, are sent out of the cell by exocytosis. So here's what it looks like. These are the proteins, the fact that it sheds the proteins, and here's the stuff it brought in. It ingests the substance, solid, liquid, somewhere in between. It fuses, we call that, another term you'll see, they'll call this an endosome. I don't get excited over that. But here, this is what happens. This is that lysosome. The lysosome and what they're calling an endosome, basically the little packet, the vesicle, has the stuff that came in fused. Okay, if that case is going to be either digested or destroyed, one way, shape, or the other, it's going to be utilized by the cell if it can be, and if not, it's going to be discarded. And if it's something that was dangerous, hopefully whatever is discarded is safely discarded. Not always the case, but that's another lecture entirely. Here, this is as though transcytosis means it started here, went here, it came in like this, it left like this. Basically, the cell is just a corridor for it to go through. So the membrane around it, and that's what I was trying to demonstrate badly before, they're called false feet or pseudopods. And again, this is what collectively, this is amoeboid motion. Most people who came from high school looked at pond water. You saw things that were moving around in there, spinning and doing stuff like that. Amoeba were very, very large, and basically this is how they move. Now, our white blood cells, classically, they use amoeboid motion. So the cytoplasm flows into those temporary extensions. They're showing it. So this is where the fact that this, what they're trying to represent here, is that it triggered these receptors, and in doing so caused these extensions to form. Cytoplasm flowed in, and eventually it brought them together. As you can sort of see, that's where it's heading. And in the cases that in membrane. Membrane is wonderful like that, in the fact that it's flexible and fluid, and you can pinch a little piece coming in. And you'll see illustrations in various texts. I use one in micro all the time, actually showing you how things are spit out, the membrane. And it's quite remarkable when you see that. It's a lot of one of the ways that bacteria and viruses can be spit out of a cell. Pinocytosis, the only thing that's different is the fact that you're using fluids or oils, and they bring a very important thing to light here. It's called sampling the environment. We are constantly, you got it in lab. You talked about lining tissues. You talked about skin. The epidermis of the skin, which is in contact with the outside. Okay, you have keratinocytes, melanocytes, Merkel cells, and you have something called the dendritic cell or Langerhans cell. Those are actual parts of your immune system. Their job is to have these, we call them dendritic because they have lots and lots of little tentacle-like projections, kind of like a tree. It's lost its leaves, so we're going to see entirely too many of them. And what they do is they're constantly sending out little branches to the exterior and grabbing onto something. And what it does is it allows your immune system to recognize any changes and constantly be on guard. It's like keeping it in tune. Human bodies, brains, physical portion of your body, the mental part of your body, the intellectual part of your body, all of that is subject to, basically, very simple, use it or lose it. If your muscles deteriorate if we don't use them. End of the day, the voice is going. Use it or lose it. Muscles will deteriorate. A muscle in a cast for a long period of time. Fortunately, once you start to use it, it'll come back unless it has been disused. We call it atrophy of disuse. Okay. Your brain is like that. It's very easy for folks as they get older to kind of stop using it and edge out. Like that. My mom did crossword puzzles until she was 87, 88 years old. She could easily beat me in Scrabble at 88, and I have a pretty good vocabulary. I was third in my household. My mom, who never set foot in a college door, was first. My sister, who was a high school English teacher, so she went back and got her MBA and went to the business world, was second. I was third. We had that household. And really, my mom was intellectually, I told this the second time today, was intellectually very, very sharp till maybe 88 to 89 years old. Once Alzheimer's set in, it was just great. But by 93, that's a good long life, no complaints. But it's that kind of a thing. And I firmly believe that too. So I'm doing what I'm doing. We do this thing because effectively interacting with you folks keep us sharp. The same thing when I was a doctor and had residents, students who were young doctors who were working on me, and medical students. I keep you sharp. Kind of questions that are there. So you have to be up on what you're talking about. And I sincerely believe that. And this is an example. So your immune system is constantly doing, and your intestines doing the same thing. Most of the stuff that comes in your digestive tract is in that sort of fluid phase. It's less likely to be solid than it is to be liquid. And again, membrane is recycled, and they're just showing it to you. The interesting thing about receptor-mediated endocytosis is what's going on. It's a very specific process. Everybody in this room has a parent, a grandparent, a relative, somebody older in your orbit who's taking something called statins. Statins are medications. Oh, the doctor put me on it because my cholesterol was high. It's really not the case, but I think you get the idea. Okay. Basically, one of the things a lot of people, the reason that they have problems with it has to do with their lifestyle. It's their diet, their lack of exercise, perhaps they smoke, perhaps they drink, but we pick something like that. And most of the time, the way we control these things are lifestyle alterations. You're looking at someone. Change my wicked ways most of the time. That eating thing still gets in the way. Pretty good, too. There's this little hole in the wall that's getting popular Mexican restaurant up in Zelienople. That's good. That's where she wants to go. I'll try. And so all that aside, this is an example. You may know someone's been told, oh, I have this bad cholesterol. It's called LDLs. They call it the bad cholesterol. Really not cholesterol. It's a complex of fat with cholesterol in it. Normally, you have to have these receptors. If you don't have them, it's a genetic defect. You can't bring them in and process them. So when they're flowing in your bloodstream, which they will, if you can't bring them into cell, you have an excessive amount in your bloodstream. And your bloodstream, your capillaries, small arteries and veins are constantly being repaired. They have little ruts and irregularities that constantly have to be remade all the time. In that process, when they're damaged until they're repaired, it's very easy for these fatty molecules to attach to them and start an inflammatory process. It's the foundation of hardening of the arteries, atherosclerosis. So these folks, we have something called hyperlipidemias. Emia means in the bloodstream, lipid means fat, hyper means too many. And these hyperlipidemias are genetically based. That's specifically about what they call these clathrin-coated pits. I go into it in a lot of detail with the advanced classes. I want you to be familiar with it. It's sort of a special branch of receptor-mediated endocytosis. And the best example for students are these people with hereditary problems processing fats. They can't get them into the cell. They don't have the proper receptors. Other things, okay, insulin comes in this way. Unfortunately, viruses, diphtheria, and cholera toxins may be taken in this way. We'll get to caveolae. We talk about smooth muscle. We'll skip it for now. But notice, tetanus toxin can get in this way. If you did not know, when you get immunized for tetanus, you're being immunized not just for tetanus toxin, but also for diphtheria. It's a trivalent immunization you get. It's called DTaP. Diphtheria, tetanus, and what's called acellular pertussis, which is whooping cough. You get 3 for 1. Most people are not at risk of any of those. What you're trying to do is make sure that they're protected. And just in case they would go a long time or be someplace where they were unable to get the protection should something befall them. Typically, that's someone's out camping in the wilderness and has a tetanus-prone wound, and if their tetanus is not current, they can be in big trouble. The immunization doesn't stop you from getting it. It's a preventative measure. If you're out of touch with your immunity, we do this in micro. with immunizations, you're in big trouble. Diphtheria is nasty, very nasty. We very, very, very rarely see it in this country. Here they're showing it to you. Receptor-mediated endocytosis, contacting the receptors, there it is. And effectively, now, something been processed, it has to go to another cell, we have to secrete it, or exocytosis. So whether I'm producing mucus now, whether I'm producing saliva now, whether I'm perspiring now, those are all by definition secretions. Fluids that are being released, or somewhat solid fluids, or thicker fluids, or materials being put out of cells. So we call that a secretory, secretory. And that kind of vesicle, where we put that stuff in so it doesn't deteriorate in the cell, is called a secretory vesicle. And the example we're going to talk about has to do with neurotransmitters, the way your nervous system tells your muscle to contract or not contract is through a chemical. The way your nerves talk to each other in your brain is basically by chemical. You're hearing my voice, processing what I'm having to say, and hopefully understanding it is all about nerves talking to each other, and that conversation involves the release of chemicals. Chemicals generically are referred to as neurotransmitters. So you are now collectively neurotransmitting. So all of those things, the waste materials, are exocytosed. The mucus, other things. Your insulin, which is a hormone, is exocytosed from your pancreas. All the same thing. It's encased in membrane. The membrane protects it until it's ready to be spit out. All these people. And there's a lot of different signals that control it, but that's not the point for here. What is here is these two things, V snares and T snares. You don't really have to know about it. It gives you an idea of how intricate the process is. This is a secretory vesicle, two-dimensional view. What happens is, we call it a V snare. It's proteins that project, the V is for vesicle. How they get to the membrane has proteins called T snare proteins, very similar, that are able to, and eventually you'll see when they meet and snare or intertwine, they're going to pull or transit the vesicle to the membrane. Here they are fusing or snaring. So it's a snare in the sense of they intertwining, and they've just gotten the name snare protein. It has a more, how should I say, scientific acronym. So it's easier just to say snare proteins because you certainly don't have to know it. And then what happens is it finally gets pulled to the membrane. It causes the membranes begin to fuse. The vesicle's membrane, remember I told you membrane's conserved, fuses with the cell membrane, and voila, we get a tiny opening. And eventually, when the membrane fuses, it's not actively spitting it out. As the membranes join, you're going to see what happens next is now the membrane from the vesicle becomes part of the cell membrane, and inevitably, whatever is contained within it is secreted or expelled. Anyway, spat out, shot out. Pick something that works for you. That's a real microbe. So you can see the two-dimensional version, and here you can see the micrograph, and imagine all those particles. I mean, those could be filled with proteins. Proteins are super tiny in the giant scheme of things. And we're talking about molecules. Super tiny. This is magnified 100,000 times. So here's the context. And this is a cart before the horse. I'll give this to you again, and hopefully you'll remember it when we talk about the neuromuscular junction. There is a toxin, a nasty chemical made by bacteria, one of the worst we know. And what it does is it interferes specifically here. It doesn't allow the snares to fuse. Those two proteins can't come together. It prevents a neurotransmitter, which you're going to come to know is called acetylcholine down the road. And that's the one that basically goes from our nerves and tells our muscles to contract. Yet we take this horrible substance, okay, because when your muscles don't contract and they're unable to do so, we have a word for it, paralysis. This paralyzing toxin. We refine it into tiny, tiny amounts, millions of millions of a gram, called micros. And that's what a millionth of a gram is, a microgram. And yet we utilize it therapeutically to selectively paralyze muscles and for other purposes. It's very famous. It's used extensively. Somebody's having this done right now. So we actually inject it in them. Anybody got an idea? Each class needed a hint. It is used cosmetically, famously. Was injected famously cosmetically into people. Cosmetically means makes them look better. You should know. It's a toxin. It's a toxin. Famous name. Botox. Okay? Not that I'm suggesting that anybody needs a Botox injection. But, so, again, that's a relevant question when we do the neuromuscular junction. That's not this exam, not the exam you're going to take on Wednesday, nor this material or this exam, which is exam number 2. Now we're at exam number 3. I'm trying to give you some context for why this stuff is so important. This is what that animation was all about. Understanding what goes on with resting membrane. Resting membrane potential is just that. It is, each of the cells have that minus 70 millivolts. The big deal is whether or not it's a nerve or a muscle cell. It can change so rapidly as to send that signal we were just talking about in such a way. That signal is something that, for instance, that Botox would not allow that chemical to escape and effectively create the signal that would cause the muscle cell to eventually contract. So all cells have it. Not all cells can change rapidly. Those cells are what we call reactive cells. Okay, nerve and muscle cells are one. So, and again, the fact that you can measure it across the membrane, the difference in charge is referred to as voltage, and because we have that, we refer to the term polarity. You learned about that in lab when you had epithelial cells. You had a basal end and an apical end. Effectively, the cells, because they weren't identical on both sides. That's what meant by being polarity. Here it's referring to charge. So we don't have to go through it again. The big player, that's why doctors, nurses go wild about potassium. Potassium is the key player. There's so many of those potassium leak channels that it's almost impossible to generate any stability in the resting membrane potential without having the proper amount of sodium. You have a very limited window. In sodium, you have a fairly big window, what we call normal. Potassium is very tiny, and calcium is very tiny. Those kinds of molecules, particularly those particular sodium and calcium, and to a lesser extent magnesium, it's very, very easy. Very, very easy for something to go wrong in the cell. So we get very excited about it. When we learn about nerve and muscle cells, and moreover, in AP2, when you learn about cardiac function, you're worried because irregularities in potassium can lead to arrhythmias, they can lead to heart attacks, they can lead to somebody having to be defibrillated. That's where this comes from. And if it's in the other direction, it can basically cause the heart to stop beating also. One would be an irregular beat or a rapid beat, and one would be no beat at all. So again, excesses on either side. In other words, it's a very, very limited window where it has to be. It's kind of like pH in that regard. I mean, it doesn't seem like a very big margin, but if you go outside the margin, we're in trouble. So all of that, again, potassium has more of those leak channels, and eventually, without replaying that animation. You all can see it a number of times. Okay, we get to minus 70. As you'll see here, chloride is less of an influence. So it's right along the membrane. Always positive on the outside. That positivity is due more to the fact about being negative on the inside. I mean, it's the fact that there's a difference between balance on the inside of the membrane and the outside of the membrane. Most of the reason it exists isn't because, oh, there's so many sodiums or there's so many potassium. It exists because of that. Proteins are huge. Proteins are made of amino acids. By definition, they have this. C double bond OH. Every one, every amino acid has them. By definition, that's an acid. When you dissolve that in water, and the inside of the cell is full of water, as is the outside, the aqueous environment, amino acids do, they give up a proton. So that H separates as H plus, and what's left there is that C double bond O. It has a minus charge. So the protons have escaped. You can see the big A with a minus charge indicates they're anionic, meaning they're negatively charged. That overwhelms the system. It can't be offset by the number of potassium. Indeed, it helps potassium stay in there, but that's really the anion, so we're creating negativity, relatively speaking, on the inside, to the positivity on the outside. Because in this area, effectively they neutralize each other. Outside they neutralize each other. Right against the membrane they do not. That's really what accounts for the resting membrane potential. For instance, chloride, there are channels for chloride to move. We don't really utilize those. There are certain things, chemicals called sedative hypnotics. If somebody has trouble going to sleep, we open chloride channels. Alcohol works by opening chloride channels. That's why we call it a depressant. It makes the cell less likely to fire, particularly in nervous systems. So, I mean, that's what you're getting to with this, and we will do that part here in the last third of the class. So you start to learn about how those things work. Okay, and that prepares a lot of you who are going to take pharmacology about how they work. It has to do with chloride channels. It has to do with a particular neurotransmitter called gamma aminobutyric acid. We always say GABA, it's too hard to say the other one. You're going to get that. This is the background. More background, more background, more background. Again, that 3-to-2 relationship. And remember, it's an equilibrium. One of those channels are open for sodium and potassium. They're constantly moving. So there's always more potassium inside and sodium outside. So the potassium is always going to it's always going to move out a little bit. And the sodium is going to always move in a little bit. What continues to make sure that what accounts for that always being the case are those pumps. So even in a relatively inactive cell, there's still a flow of sodium in and potassium out. And so there's that sodium potassium pump to restore that gradient. So always make sure you have a substantially larger amount of potassium on the inside and sodium out on the outside. We'll spit out 3 sodiums and bring back in 2 potassiums. That's what this is saying. And that accounts for the resting membrane. And when we're done with this section, my voice will survive yet. The cells interact with their environment by responding directly to other cells or indirectly to extracellular chemicals. That's what they're saying. Okay? So, on the exam on Wednesday, cell adhesion moment. Not in this context, but elsewhere. So the cell adhesion molecules, there are 3 types. They basically create 3 types of structures that hold cells in some way, shape, or form together. Number 1, the strongest, called desmosomes. We went over this before. The desmosomes are reinforced by keratin fibers, that same structural protein, skin and nails and hair. It's almost like they describe it like being riveted, like a zipper holding things, an interlocking zipper with teeth. They have those little plaques, so it's a very strong union. The ones that create that have little openings are called gap junctions or connexons. They have little openings, and that allows charged particles or chemicals, and effectively, even though the cells are joined, they can remain in contact or communication with each other. So it's a different kind of ring. And lastly, tight junctions, and that means watertight. Basically, they're around the cells like a series of belts, and the belts are held together. The more of those that you have, the less likely. It's not about getting through the cell, it's getting between the cells. And there are a lot of areas where you want limited ability for that to happen. Stomach lining, because it would be acid, and it would be destructive. In the brain, because water-soluble things can impact the brain adversely. But that's why these things are important going forward. Those are the cell adhesion molecules, and a lot of this is based on the sugars we call the sugar shell or glycocalyx. Those sugars that are protruding or a part of proteins we call glycoproteins, sugar proteins. So, and there's so many of them. And that's how the fibers in connective tissue attach. That's how cells are constantly moving over one another. It's not like magic, they get out of the way. Basically, the cells are so flexible they can change shape relatively easily. And they slide over each other. And as long as the cells recognize one another by these sugars that project, it doesn't trigger what we call an immunological reaction. Your immune system doesn't go, wait a minute, you're not supposed to be here. I don't even know who you are. It's like the invader in the house comes. Your ring system goes off, whatever. See, we had a wonderful dog years ago. Loved everybody. But when he was off duty, when it was bedtime, he'd come in bed with us, and he would be off duty. And honest to goodness, my stepdaughter and her boyfriend were living upstairs. And I don't know where it happened. All of a sudden, we came in, they were somewhere else, we were somewhere else. All of a sudden, somebody shot down the stairs and literally grabbed my stepdaughter's purse. She'd done that. This gal, she's a drug sneaker, and done this all over our neighborhood. And most people knew who it was. And eventually, they caught the person. They went to jail. That's the story. We're in bed with the bedroom door closed in the master bedroom. Awake. The dog's with us, not a bark. Normally, if somebody came to the door, he'd bark at them. There's somebody in the house. He doesn't even bark. It's like you literally go, hey, it's after 11. I'm off duty. The current dog would bark, believe me. But he would show them where the valuables are, such as, oh, here. This is where the jewelry is. Woof, woof, woof. Pet me. Be nice to me. But in defense of the other dog, who was named Ralph, cute little, actually a Springer Doodle, masquerading as a cockapoo, but he was large. He found the cat, but the cat was lost. Nevertheless, back to this. If you didn't know it, all of these molecules play roles. So the next time you stub your toe, cut yourself or burn yourself in the kitchen, twist an ankle because you're running around too fast, bump yourself in a little break in the skin. The fact that it hurts and the fact that it's repaired has to do with the same process. Effectively, what happens, cells release chemicals. Those lysosomes with all those enzymes, when a cell is disrupted, they spit out. And that's what causes inflammation and pain. At the same time, it releases chemicals called cytokines. Cyto for cell, kines for motion. And what that means when we talk about a cytokine means that it will basically call those chemical signals, will attract white blood cells to an area that is, for some reason, damaged, invaded, whatever. What happens when you get a virus or a bacterial infection? White blood cells come to the party. They're trying to control the process. All of that is from these same kind of molecules. Okay, again, interacting with tight junctions, transmitting signals, directing cells where to go and what they're supposed to do. We don't understand a lot of that. So it's like I was referring to the other group today earlier. It's like stem cell technology. We don't know why cells that when someone's born, and that's why people, if you do not know why they collect cord blood and will freeze it, because in the hopes that maybe for their baby they will do that, that maybe X amount of time later, 20 years, 40 years, 60 years later, maybe they need a kidney transplant or a liver transplant. They will have the technology to be able to grow those, because the cord blood you should have cells that have the capacity to change into everything. So then, and I'll have more anecdotes about that as time goes on. But I mean, there's so much we don't understand. They'd be experimenting with these with electrical signals and chemicals and trying to find out. That's somewhat controversial, as to how we obtain those. I mean, it's kind of like we're tinkering with living cells. I mean, it's where ethics and science kind of meet, and there's again, it's not something I don't have the expertise to comment on or entertain debate. So a lot of people are anti that and pro that, but that's the nature of life. Yeah. And so obviously, basically the way our cells recognize each other is contact. They are continuously rolling over each other, and and as long as the structures are recognized, meaning not that the cell knows or visualizes it, as long as it goes over these proteins that are by their very nature receptors, and what they're designed to do is if there's an irregularity, it's supposed to be shaped like that, and all of a sudden it's shaped like this, it'll latch onto it and it'll start this immunologic process. It will cause various types of things. Chemicals will signal. Okay, in general, we call these chemicals ligands. We're almost done with the first half presentation. And so they can cause lots of different responses. It can cause proteins to change shape. The whole idea of this, we have fat-soluble molecules. They're small. They can get through the membrane. Typically, the way insulin works, the way human growth hormone works, it's through something called G proteins. G proteins, okay, you read the big G stands for guanine. Remember, this is where you build on a nucleotide. Guanine is similar chemically to adenine. So ATP is adenine, ribose, and phosphates. So the name for this is adenosine triphosphate, ATP. And the high energy bonds and all the stuff explained before. GTP is another molecule that's almost identical. Adenine and guanine are like first cousins, they're brother and sister, if you want to think of it that way. Genetically very close to one another. Okay, chemical structures rather, very, very close to one another. So when they talk about G proteins, okay, it has to do with something called GTP. And it's interesting, so the way we do it, when something like insulin or growth hormone, which does multiple things in the cell, contacts the receptors, we call it the first messenger. It's like knocking on the door. It's too big to get into the door, but it can cause changes on the inside. So that's the first messenger. After that, it triggers a chain reaction. They depict it as a relay race. And eventually, to accomplish what it needs to do in the cell, opening passageways for glucose, increasing the rate of mitosis, utilizing glucose as an energy source to fuel these extra activities, doing cell reparations. Those are all mediated by what we call a second messenger. And typically that's when the ATP, when it loses its phosphates, it becomes AMP, adenosine monophosphate. And what it can do is it kind of can change shape and sort of encircle itself. We give it the name cyclic AMP. And that, along with calcium, are, and this is the term that's important for you to know down the road, second messengers. The first messenger can't get into the cell, and it expresses this message by second messengers that are outside the cell. There are the second messengers that are already inside the cell. And they always show you these things are hard. Here's the insulin, called a ligand or a chemical. This is the G protein. Why is it a G protein? Because it activates this GTP, GTP pathway. If you magnify this, they use the relay race sort of analogy. And so this causes a shape change in here. That shape change changes the shape here, changes the shape here, changes the shape here, until finally it contacts some enzyme, some triggering enzyme, and that causes the release of these second messengers like cyclic AMP or calcium. And they create this cascade of events. This is what happens to insulin. When you get to diabetes, you'll look at it a little bit more closely in AP2. So it's a well-known mechanism, but I mean, I'm not going to ask you to go through chapter and verse of all the steps. Just eventually, you're going to see this again. You're going to see it when you get to endocrine. You're going to see it in other passages. This repeats itself frequently in this text. Okay, it is now 4:16. Give my voice 10 minutes. Figure 4:25, 4:26, and we will resume. Thank you. Stop this recording tentatively and